It's good. All of these wires. Yeah, really sad. That's happened.
Okay, good. And the Zoom is running as far as.
Yep.
And is the CCP
Oh, yeah,
Zoom
we gotta delete or close that screen. Sorry, Lance. Did you say something else?
It's a regular little URL.
Yeah, yeah, the standard CCPP event.
Okay.
Yeah.
I hope my can know that.
It's
Well,
all
look
good.
at this is an amazing,
Snowden.
amazing crowd. It's a real pleasure that Sam Hadden is here with us and giving an Astro seminar, but one intended to also communicate with the people in Quran. I could go through your biography, I suppose. It would test my memory. He was a student at undergraduate at Purdue, then went to Chicago for graduate school. Sorry, it was the city of Chicago,
city of
it's not
Chicago.
the university.
Yeah, that's right.
Thinking about all that wind and snow.
That's right.
And then went for a postdoc at CFA, the Center for Astrophysics at Harvard, and now is at CETA, Center for
Canadian Institute.
a Canadian, yeah,
Yeah.
thank you. The Institute for Theoretical Astrophysics in Toronto, a very eminent place. Thank you very much.
Yeah, great. So great. It's I'm excited to be here today and talk to you about some of my research. So a lot of my research focuses on the theory of dynamical systems and its applications to the solar system and exoplanets. And Newtonian gravitational dynamics has been one of our most remarkably successful mathematical models for reality, and we've used it for centuries to learn all sorts of stuff about our solar system. And now in the exoplanet era, it's a tool whose predictions we can use to learn all sorts of precise information about alien worlds that are hundreds or thousands of light years from our own solar system. And the topic that I'll be discussing today, which is causes and consequences of chaos in planetary systems, I think really underscores the value of understanding the sort of mathematical theory undergirding Newtonian dynamics for answering some of our most pressing questions in both planetary, exoplanetary, and solar system science. Let's see, advance. Okay, first I just want to start with a little bit of history. So in 1889, there is an international prize competition announced in honor of King Oscar II of Norway and Sweden's 60th birthday. The competition is organized by Gauss-Dimittag Leffler and solicits submissions from mathematicians on a series of 4 questions. The first question of which is basically to solve the Newtonian in-body problem by means of some series solution. And there was a sense at the time that this sort of solution was within reach given the success of a lot of the analytic methods that were popular among astronomers at the time. And of course, the idea was this would greatly extend our understanding of the solar system. So Henri Poincaré submits the prize-winning memoir in this competition, in which he lays out a lot of foundational ideas in dynamical systems, and actually in his winning memoir purports to have discovered or demonstrated such a series solution, at least in the case of the so-called restricted 3-body problem that he considered a special case of the n-body problem. However, while preparing this memoir for publication, he discovers a critical error that leads him down a road to ultimately discovering what we would refer to today as a so-called homoclinic tangle. This is a mathematical structure that really plays a fundamental role in giving rise to dynamical chaos in a broad class of systems. So this is really the discovery of dynamical chaos found while investigating the planetary n-body problem. And so while Poincaré shows that planetary systems can exhibit dynamical chaos, it's not until nearly a century later that we understand the dynamical nature of our own solar system, and we have to wait for modern computers to come along capable of running long-term numerical simulations. And a series of results come out in the late 80s and early 90s that show that, in fact, our own solar system exhibits dynamical chaos on sort of million-year timescales. And perhaps most intriguingly of all, in 1994, Jacques Lescar shows that on billion-year timescales, it's even possible for Mercury's orbit to basically become so eccentric that it will collide with one of the other terrestrial planets. And interestingly, Lascar's results weren't derived with direct numerical integrations, but rather so-called averaged equations of motion. They're really a sort of computational implementation of some mathematical ideas going all the way back to Poincaré. And I'll try to argue in this talk that making breakthroughs on some of the contemporary problems we're facing in both exoplanetary and solar system science require some similar new sorts of computational implementations of mathematical theory. Okay, so let's see that. So it's actually not until 2009 that computers catch up and we're capable, and we confirm basically Lascar's results by direct numerical integration. So a paper came out in 2009 by Lascar and Gastineau showing that over the next 5 billion years, this is the target they set because that's basically the remainder of our sun's main sequence lifetime before it will turn into a red giant and engulf the terrestrial planets, that there's a 1% chance that Mercury can become unstable and collide with one of our other terrestrial planets. And so what I'm showing here is a plot from their paper showing the evolution of Mercury's orbital eccentricity. And since I'll be talking about orbits a lot in this talk, I better define some terms just so we're all on the same page. So a planet's Keplerian orbit is described by its semi-major axis. A is often denoted just sets the size of an orbit, and the eccentricity E, which defines how elongated the orbit is. And so this is a series of 2,500 direct simulations of the solar system that they did. The only difference between the simulations being that they've moved Mercury by a few millimeters for the initial conditions in each simulation. And you can see after a few dozen millions of years, the trajectories all diverge from one another and sort of wander quasi-randomly. And occasionally, every once in a while, an unlucky Mercury gets so eccentric and shoots up that it will ultimately end up running into some other unlucky terrestrial planet.
And the current eccentricity of Mercury is 0.3?
0.2, I think. But it changes
But
over
it's in that
lots of
band.
degrees. It's in that band, yeah. So it for most of the time, we can look at this one too, yeah. It starts at 0.2. Most of the time it stays below 0.4. Since John is here, I have to mention some of our own recent results as well. Not only is there a 1% chance that Mercury could be stabilized in 5 billion years, but there's even a chance it can become destabilized in as soon as 2 billion years. This was some work we did combining direct numerical simulations with rare event sampling techniques. But I think you can rest assured that we're probably safe. The odds of this happening are about a part in 10,000. Okay. So it's fun to think about, the distant future of our solar system, but in all likelihood, we won't be around to see it. And it's satisfying to have an answer to the long-standing question dating all the way back to Newton, at least, of whether the solar system is stable, a probabilistic answer, albeit. But I think really the key aspect, scientific aspect of these results is what they say about our solar system's past and how we got here. What does it mean that we're in this sort of dynamically delicate state where our solar system can be unstable, but only if you look at its evolution on timescales similar to its present age. It would have, of course, been quite shocking to, yes?
I think you have a question on Zoom.
Oh.
But that person would need to speak up.
Hi, can you hear me? Sorry,
Yes.
I couldn't attend the talk. I'm sorry, so I'm on Zoom. I think you can now see me, probably hear me. I wanted to ask a question with respect to what you said before.
Could you identify yourself, because the people in the audience can't.
Okay, this is Eric van den Einden. Hello.
Yeah, hello.
Hi. So you're talking about probability of escape or collision, but probability with respect to what exactly? These systems are deterministic, so is respect to randomization of the initial condition, I guess. But how do you randomize them? And how does the answer depend on what you do initially?
So I'll talk more about this later, but it's in the nature of dynamical chaos that basically no matter how precisely we measure. I mentioned the simulations earlier where they displaced Mercury by a millimeter. I should have said that that's much smaller than the precision to which we actually know the position of Mercury. So any sort of physical offset, it doesn't really matter how, how close you start them. The effects of chaos are to amplify any tiny differences in initial conditions. So when we talk about probabilities, we mean, given the information we have about the state of the system we have today, practically you run an ensemble of trajectories within the precision to which you know actual positions, and you say which of these, what fraction of those are unstable. So that's what I mean. Does that answer your question?
Yes, but not completely, because so if you were to redo the simulation with a different perturbation, you're telling me that you would get the same probability?
I'm saying if I did 100,000 simulations and I displaced Mercury by a few millimeters of machine precision on my computer, then I would get, of those 100,000, 1% of them would go unstable in a billion years, for example. And so we can only make probabilistic statements about the future behavior of chaotic systems beyond the sort of timescale set by, we'll talk about it later, but the Lyapunov time, which is how the timescale on which initial perturbations sort of balloon to beyond our ability to keep track of.
You're stepping on dangerous ground when you talk about probabilities, because from a mathematical perspective, there's this whole thing about measure theory, and I think what I would say is that you're talking about kind of a posterior probability under some kind of very optimistic assumptions about our current knowledge.
Let's go with posterior probability.
And so-
I think that Eric's point was that if you displace it by 3 millimeter, probabilities will change. It won't be the same probability.
Yeah, his point is
Right.
that if you change the displacement, like the maximum displacement to be like 1 millimeter, or you make it 2 millimeters, do you get the same probability out there?
Yes.
Yeah, that's what I was asking.
Why? I mean,
That's the question.
why? I don't think you do.
Yeah, you do, I think.
Why do you? Why do you?
Okay, that's your job to explain that. Let's let it go on.
Okay.
It's like you're good.
Thanks,
It's like
Eric. That was
you're
great.
Thank you.
It's not actually mixing. So yeah, this is a
like
whole
organic
rabbit hole of dynamical systems. Yeah.
Maybe Florence.
Right. Okay. So why are we on this dynamically delicate state? We could have found ourselves. It would have been shocking to be in a solar system that's 5 billion years old and about to go unstable in say 1,000 or 1,000,000 years. But there's no reason a priori we couldn't have found ourselves in a solar system that exhibits typical dynamical lifetimes of trillions of years or more. And of course, one natural way to find ourselves in this sort of delicate state is if our present day solar system has descended from former versions of itself that had more planets and as a consequence were more unstable due to the presence of those planets, which were then lost through collisions. And so, you can sort of trace this line of reasoning back through the evolution of the solar system and imagine that at every stage in its evolution, it's sort of in this metastable state where it's dynamically unstable, but only if you look at its evolution on timescales of its present lifetime. And more generally, this might be an organizing principle of how planetary systems form and evolve. Okay.
Did you talk about the Lyapunov exponent?
I have not yet. Yes. Okay. Speaking of other planetary systems, it's sort of an amusing coincidence that this, for the first time, we're able to actually follow the remainder of our planetary system's evolution for the remainder of the sun's main sequence lifetime is the same year that NASA launched its Kepler mission, which led to an absolute explosion in the number of exoplanetary systems that we now have to think about and compare our solar system against. And, perhaps the key result of missions like Kepler and the decades of exoplanet discoveries prior to that has been to reveal an amazing diversity of planetary systems, which one can appreciate, for example, by looking where they fall in this plot of planet mass versus orbital period. And we find planets scattered all over this parameter space and very frequently in places where we have no analogs in our own solar system. Oh, yeah.
Is there some relevance to that horizontal line?
Yeah, so this is an artifact of the way, so for, we don't always measure everything about planets. Sometimes we measure their size, but we don't know their mass. Sometimes we measure their mass, but we don't know their size. And so what they've done is they just assigned everything that's roughly Jupiter size to be Jupiter mass. I think that's, yeah. So, it's to order of magnitude. You can't put everything we've discovered on the same plot because we don't have the same information about every planet. Right, okay. So one of the central goals of exoplanetary science, of course, is to come up with theories of planet formation and evolution that can account for the diversity of planetary systems we see and understand where our own solar system fits in with this broader context. Why, for example, do we not have some of these other types of planets that we find around other stars? And we do this by going out first and detecting planets and measuring properties about them. And the question is, what do these properties really tell us about how these planetary systems formed and evolved? And planets are assembled in a relatively brief phase of their host star's lifetime, the protoplanetary disk phase, when there's lots of gas and dust around. But then we have to contend with billions of years after that formation of these planetary systems undergoing essentially just pure Newtonian gravitational dynamics.
Some people in the audience may not know the age of the solar system.
I should say, yes, our solar system is 5 billion years old, roughly. And yeah, so this is a brief fraction of the formation stages, a small, tiny part of our lifetime. Right. And so I think the lesson from our solar system is things can potentially change dramatically over this ensuing billions of years. And so if we want to understand the full history of these systems, we need to understand how they're shaped throughout their evolution. And so for the remainder of the talk, I'll start out by reviewing some of the evidence that indeed the planets that we detect today have been shaped to a great degree by their dynamical evolution following their initial formation. And I'll argue that in order to understand how these systems have evolved over time, that we really need a better theory of how chaotic dynamics and instabilities play out in these planetary systems in order to understand them. And then finally, I'll conclude by talking about what I think are some exciting opportunities going forward as the sort of exoplanet detection frontier starts pushing out into the outskirts of planetary systems in regions where we haven't detected planets with current methods, and where I think dynamics can play a key role in learning the sort of things we want to know about those planets. Okay. Right, so the first evidence that dynamics plays an important role in shaping planetary systems came from measuring orbital eccentricities of giant planets detected by the so-called radial velocity method. So I'm plotting giant planets greater than about a third the mass of Jupiter in this plane of orbital period versus eccentricity. And the thing that you notice immediately is that they're sort of dispersed all over in terms of their eccentricity. And many of them are on quite elongated orbits relative to our own Jupiter and Saturn with their measly eccentricities of about 0.05. So Jupiter and Saturn are on very circular orbits. And we think that gas giant planets like Jupiter and Saturn, we know they have to form when there's lots of gas around because they're mostly gas. And the interactions with the gas disk in which they form should leave them on quasi-circular orbits. And so the fact that so many of these are on such eccentric orbits really points to some sort of dynamical shakeup happening after these planets have formed. And indeed, a number of studies have shown that the eccentricity distribution of these planets can be well reproduced by invoking planet-planet instabilities and scattering after they form.
Would there be some sort of observational bias, possibly? That
Yeah,
it's
there's
easier to see the ones that high in eccentric orbits.
It's I think it's typically, yeah, because you get sort of sharp spikes in the radial velocity as something swings through pericenter. So yeah, there's definitely bias that goes into this plot, but just the fact that we detect so many with such extreme eccentricities means it has to be playing out in some of these systems at least.
Right, but it'd be nice to understand what the plot would look like without the observation of bias. Do you have any idea? Or have you thought about how?
That is it's a especially tricky problem with radial velocities because it's been done for such a long time with such a heterogeneous sort of group of surveys. So the way to do it would be to go out and design a survey for which you could, characterize very carefully its detection efficiencies and that sort of stuff, and then you could try to debias your results. So yeah,
You're saying that hasn't been done?
Can't be done right now.
It can't really be done right now. Yeah. I'm trying to think of particular surveys that are closest to that. Maybe.
That's okay. I didn't mean to.
Yeah, no. It's a tricky problem.
Like the sort of thing you could model.
It's because these detections come from just so many different teams, and there's human factors about people chasing.
Well, that's true, but I was trying to think of some more pipeline type of.
Yeah. I mean, it would take, I think, designing a survey from the beginning to be able to do that sort of thing. Question?
When you say planet-planet scattering, do you mean like literally the planets are hitting each other, or is there?
Oh no, sorry. I mean gravitational scattering. Yeah. So they. I'll talk about this towards the end, but these planets basically don't run into each other. Yes. Okay. So I want to turn from these giant planets to the sort of class of planets that dominates today's known exoplanet population, and these are the so-called transiting or sub-Neptune planets, and we have thousands of these now thanks to Kepler, and I'll often slip into calling them Kepler planets probably, but I should note that NASA's TESS mission also is contributing to this sample of planets, but these are basically planets that are on orbits that put them, they go around their star between 1 and 100 days. For reference, Mercury, the closest planet to the sun, is on an 88-day orbit. So these are mostly interior to our innermost planet, and they're intermediate in size between the Earth and Neptune, and we don't have any of those in our own solar system either. And I'd say really the key result of the last decade of exoplanet science has been the discovery that, despite their conspicuous absence from our own solar system, these types of planets are everywhere. I'm
sort of confused. You described it in terms of radius, but the radius shouldn't matter of the planet.
The size of the planet.
And the size of the planet shouldn't matter, and the mass shouldn't matter.
Shouldn't matter for
the gravity, I would have thought, right?
Oh no, I'm just saying that we don't have anything this size. We don't know why are they this size.
So when you say sub-Neptunes, you mean less massive than Neptune? Or
I
mean, that's not going to be a dynamical question, is it? Because why does the mass of the thing matter for its
dynamics? The mass of the planet matters for dynamics.
Oh, okay.
Right. I'm just sub-Neptunes is sort of loosely used as a catch-all for things that sort of sit in that block between
of orbital period. So it's a
radius. Really, it's a statement about the planet size, that they're somewhere between Earth and Neptune. They can be as big as Neptune, but less massive.
I guess I'm just thinking, I understand that the dynamics would care about what else was around.
Yeah,
and
so it's the planet interaction.
The orbital radius would matter. But why the radius of the planet?
Oh, the radius? No, the radius doesn't matter for the dynamics. The radius, the mass of the planets does.
When you say planet radius, you don't mean then the
physical size of the planet?
You mean like what its orbital radius is?
So that's equivalent to its orbital period modulo the mass of the star.
You really do mean the planetary.
I do mean the planetary.
I'm just surprised that there's dynamics in that and not just.
There's not. No, there's not. Well, okay, I'm showing radii because. I'll get to masses. Okay. Right. So this is what we get for free.
You can measure.
This is what we get for free from Kepler. Yeah. Sorry. So we do have some information about the masses, but we get the radiuses most easily. Right. Yeah. So these things are around something like at least a third of sun-like stars. So how does the planet formation process produce planets that are quite different than what we find in our own solar system around stars that are relatively similar? So we do know some things about them. About half of them are observed to be in multi-planet systems. We find everything from pairs of planets around the same star to, I think the record holder now is an 8-planet system. And if you do the statistics, you find that something like the typical system has something like 3 planets orbiting within 400 days of its host star. They're often okay, yes. They're often closely spaced in the sense that the period ratio between adjacent planets, so I'm plotting the histogram of observed period ratios in these systems, peaks somewhere inside of 2 to 1. So the closest pair of planets in our own solar system is Earth and Venus, and they sit just a little outside 1.5 in their period ratio. So they're often dynamically well coupled to one another. We know that the typical mass.
Why is it peak distribution?
Why is it a peak?
Why is it peak distribution?
Yeah, so it's again.
Why is it not flat? Right. I mean, why there's a typical period ratio? Like, why is it more probable to have an Earth-Venus period ratio versus something that's completely different?
That's the question for planet formation. Yeah. So planet formation seems to make these sorts of systems with that sort of period ratio, close period ratios. I should mention there are selection effects that go into that histogram, but
this come out of simulations.
You can still.
Did you get the distribution from simulations?
You can turn a lot of knobs in simulations to get whatever you want. Is my take on it, and there's a lot of knob turning. Yeah, but I think that's an active question still that we don't know the answer to. We're still in a lot of ways at the basic fact gathering stage. Yeah, so we know their masses both from follow-up observations with radial velocity, as well as by dynamical modeling of the mutual perturbations in multi-planet systems that will manifest in the observations. That's something I've worked on extensively in the past. And that same dynamical modeling shows that their orbits are often fairly circular, with eccentricities of a few percent. That's sort of reminiscent of the values for Earth and Venus as well.
Sorry, I'm having trouble understanding the concept of sub-Neptune.
Sub-Neptune.
Thank you. Are there any sub-Neptune planets in the solar system?
No, we have.
By definition,
it's a size gap between Earth, which.
So literally the size.
So I'm literally defining.
I'm still having trouble understanding why the size of the thing matters at all.
I guess the physical size. It doesn't matter for the dynamics,
right?
But one might wonder, how do you form a planet of this size? So we know, for example, based on their masses.
Yeah, I understand why it would tell you something about how the system formed.
Yeah.
But from this, you were telling us about dynamics, and so I was struggling to see how it related to dynamics. So maybe I'm
just trying to introduce this population of planets.
But it's basically solar system-like planets. Can I think of it that way?
Well, unlike in both the respect that they're all sort of crammed up closer to their stars, and in the sense that probably not, it's not terrestrial.
Sorry, you're talking about when you say radius, you don't mean orbital radius.
No, I mean the physical radius is between Earth and Neptune. The physical radii, yeah. And so you can.
And so.
You can argue based on their masses and the radii that we see that they're probably sort of terrestrial mass, bigger, like cores that are a little bit bigger than Earth, overlaid with lots of gas, because we find that they're often fairly low density, and the only way to produce planets with the densities that we see out of physically possible materials is to overlay a bunch of hydrogen and helium on top of planetary cores. Okay, so there's evidence in these systems that they are sculpted to a significant degree by dynamics. There's multiple lines of evidence. I'm just going to mention 2 in the interest of time. And the first is based on some recent work led by a former undergraduate student at the University of Toronto, Caleb Lammers. He's now a grad student at Princeton, where he showed with numerical simulations that the so-called peas in a pod trend can be reproduced by giant impacts. And so this peas in a pod trend has been pointed out by a couple authors and sort of widely discussed in the field. And it's basically the observation that if you line up, say, some lineup of systems of Kepler planets and you look, then roughly speaking, they tend to be similar to one another in their sizes and masses, and more so than if you had just, say, drawn planets from some random global distribution. And so, this has been debated in the field. You're supposed to notice that these look like similar P's to one another in a pod. And so what Caleb showed is this sort of structure is a natural outcome of giant impacts. That is, if you start systems with more dispersed masses initially and let them evolve and they're dynamically unstable, then those dynamical instabilities will preferentially collide smaller mass planets so that everything sort of converges within a given system towards a single mass. So it tends to produce dynamical instabilities, that is, tends to produce more uniform masses in systems. And the other piece of evidence that I'll mention is that many of these systems appear to be in the sort of dynamically fragile state that we find our own solar system in. In other words, if you look at their typical masses and spacings and orbits, then you would estimate that their instability timescales are similar to their multi-billion-year ages. And so the hypothesis is that, like I sort of laid out before in the case of the solar system, that these have descended through instabilities to the systems that we see today. And I say these spacings indicate giga-year instability timescales, but this is really based on extrapolation of numerical experience. We don't actually have a good theory of what this instability limit should be. And I should say these are not direct in-body simulations of the systems that we actually see. Those are really computationally out of reach, but rather what the sort of state of the field has been up till now is to basically run large ensembles of numerical experiments and try to extract some sort of empirical scaling law for how planetary instability timescales vary as a function of, say, initial planet spacing. So I took this particular plot from the Hu and Wu 2015 paper, but you can see, lots of different authors have tried their hand at this, where they run large ensembles of numerical simulations, fit some law for they measure in their experiments how long it takes their system to go unstable, and they fit some law for how they think instability should scale. And there's at least two serious difficulties with this approach. The first is that there is, of course, a very large parameter space to explore in terms of initial planet masses and spacings and orbits. And these sort of numerical experiments have to make all sorts of simplifying assumptions, usually reducing things to equal mass, equal spacing systems when they set up these experiments. And the second problem, of course, is that this really requires extrapolation in order to apply to the sort of sub-Neptune systems that we observe. And that's because for a planet sitting at a 10-day orbit, it's gone around its star at least an order of magnitude more times than we can feasibly simulate directly on a computer. And so in order to really make sense of exoplanetary systems and understand how they've been shaped by dynamical instabilities, I would argue that we really need a theory that can describe and predict how these systems change due to chaos and instabilities. And so in the second part of the talk, I'll be discussing some of the recent success I've had working along with collaborators in starting to build this sort of theory using tools like computer-assisted Hamiltonian perturbation theory. Okay, so I should say at the outset, to be clear, that dynamical chaos in a planetary system is a necessary condition for instability to occur. The reason being that if your system is not chaotic, then the variations in the orbits of the planets in that system are necessarily going to be bounded for all time and often quite small. But it's not necessarily a sufficient condition. So, part of building this theory is both understanding when dynamical chaos will produce instabilities and the sort of timescales on which those instabilities will manifest. Okay, so I think if people have some sort of notion of what dynamical chaos is, they probably think of it in terms of sensitivity to initial conditions. That is, if you have some system and you make a small change in its initial conditions, it can produce significant changes in its behavior down the line. And this is something that we can quantify for continuous time dynamical systems like the planetary n-body problem with the so-called Lyapunov time. And so if I have some equations of motion governing, say, planetary positions and velocities as a function of time, then you can ask what happens to a trajectory that is infinitesimally nearby in your phase space, and derive an equation for how the separation vector to that trajectory evolves. And this just follows from simple Taylor expansion. And for chaotic trajectories, if you're on a chaotic trajectory, then the separation vector will grow exponentially in time, and the time scale of that growth is referred to as the Lyapunov time. So as a concrete example of what that looks like in practice, here I've just set up a simple system comprised of a 3 Earth mass planet and a pair of test particles. And the only difference between the test particles is I've displaced one position relative to the other by 1 part in 10 to the 15. So that, for scale, is a millimeter relative to the Earth-Sun separation. Yep.
Is that exponential dependence like inherent to the system, or is that just the way you're defining chaos here? Is it like
it's always exponential? Yeah, it's so yeah, it's sort of the definition of chaos that you have this exponential divergence.
Okay, so if it's like just some really sharp curve that isn't exponential, that would.
If it's polynomial, then it's not chaos. Yeah.
Okay, thanks.
Okay, so you can see these orbits initially follow each other quite closely until a sufficient number of Lyapunov times have elapsed, after which time the two particles sort of go off and wander quasi-randomly, potentially eventually reaching instability. And so the concept that I'll be sort of taking from the theory of nonlinear dynamics is the idea that in planetary systems specifically, and in sort of energy conserving classical systems more generally, chaotic motion in these systems arises from so-called resonances and their interactions with one another. And to give you a sort of rough sense of what I mean by this before going into more detail, I'm showing this plot taken from a paper with some collaborators where we set up this simple 3-planet system, which I've represented as this sort of cartoon diagram here, and made a grid of simulations. And the only thing we vary, and across this grid, we vary the periods of the inner and outer planet, keeping this middle planet treated as a test particle on a fixed orbit, so that the period ratio between both the outer pair and the inner pair are varied. And at each point on this grid, we record a Lyapunov time and color the pixel according to that measured Lyapunov time, with hot colors for shorter Lyapunov times or sort of stronger chaos. And then the white spaces are where we don't find any numerical evidence for chaos. And what you'll notice is that the sort of regions of chaotic behavior in this diagram are really structured by these bands that fall where one sees integer ratio periods between either the inner pair or outer pair, and especially where those bands intersect. Okay, so that's an idea we'll hold on to. For later, the resonances have something to do with dynamical chaos in the system. And so I now want to turn to describe some work that we should be submitting in a week or two, again led by this former undergrad student, Caleb Lammers, where we ask, what is the minimal dynamical model that we can construct that can reproduce the sort of instability time behavior that people see in the sort of numerical experiments that have been the sort of state of the field up until now. And this is our own version of such a numerical experiment. We're setting up a relatively simple system where we've just taken 5 Earth mass planets and spaced them so that the period ratio between each adjacent pair is some fixed value. We set up these systems, we integrate them, measure when they go unstable, and record as a function of that period ratio, and we get these points here. And so in order to construct this minimal dynamical model, we're going to use the Submet code. This is open source Python package that I developed for doing the sort of dynamical calculations that I'll be describing shortly. And in our model, we're only going to consider gravitational interactions between nearest neighbors. So we're going to ignore the force of gravity between more distant planets. And furthermore, we're only going to consider a small number of terms, potentially resonant terms, from this interaction potential. So we're not going to consider the full gravitational potential. And to explain exactly what I mean by this, we need to take a bit of a digression into Hamiltonian perturbation theory. And so Hamiltonian dynamical systems are a broad class of systems that describe the evolution of any sort of energy conserving classical system. And the equations of motion can be written as I've shown here. The sort of key feature is that you get the full set of equations for the phase space variables you're interested in from one single scalar function referred to as the Hamiltonian, which I've written as H. And planetary systems, of course, are one example of this class of systems, and planetary systems are really the quintessential example of what's so-called nearly integrable system, where the Hamiltonian has this special form where you can split it up into a main part, which I've denoted H0, that depends on only half of the variables, and then a perturbation part, which I've denoted as H1, which is small in some sense with respect to the main part. And so in the context of a planetary system, these various, so the J and phi variables that I've written are referred to usually as the action and angle variables. The action variables in the planetary case are related to the semi-major axes and eccentricities of the orbits. The angles are related through some esoteric celestial mechanics variables to basically the planet's angular positions and the orientations of their orbits. And this splitting of the Hamiltonian describes, the main part describes basically just the simple dynamics of non-interacting Keplerian orbits. And this perturbation term captures the dynamics induced by mutual planet-planet interactions. And so if one were to ignore planet-planet interactions, say if I set this epsilon term equal to 0, then we get fairly trivial equations of motion, which it's straightforward to show have this solution. These action variables remain constant in time, so the integrals of motion, and the angle variables just advance at a constant rate with respect to time. And so now when one considers the effects of the perturbation terms, it's helpful to write that perturbation term as a Fourier series in the angle variables, since it should be 2 pi periodic in those variables. And now we get equations of motion in which our action variables are no longer constant, but will change with time. And it's relatively straightforward to show that an approximate solution to those equations I just wrote is given by what I've shown here, ignoring higher order terms in this order parameter epsilon. Basically, the salient new feature of the solution is that the actions are no longer constant in time, but will have some additional oscillatory terms that will tend to be small and oscillate at different periods. So this is so-called quasi-periodic motion. Of course, if you're sort of paying keen attention, you might object, what about this term here? And so you can run into a so-called small denominator problem near resonances. So this is what I was talking about more specifically in the planetary problem about resonances. So these can invalidate this approximate solution, and there's really a whole rich theory about what one does with these small denominators, how one handles them, what their consequences are, that we've really just scratched the surface of here today. But this is enough to understand, for now, what we're going to do when constructing this minimal dynamical model. So back to making this minimal dynamical model for explaining instability times in planetary systems. So the first thing we're going to do is chuck out most of these terms and only care about those potentially dynamically important resonant terms. And so these resonances occur, as you might expect, where period ratios in this system, where the planet's period ratios are near integer ratios. And since about half of you are mathematicians, you should object immediately, but you're always near an integer because they're dense. And so the other thing we can use is that these coefficients become exponentially small in powers of the planet's eccentricities. So typically only a handful of them will ever be important. And in particular, you can sort of make an association between a given resonance and the order of eccentricity that appears in these coefficients. So the celestial mechanics parlance is you call a period ratio of j to j minus 1 a first order resonance. And those have terms in this disturbing or perturbing expansion that are linear in eccentricity. A j to j minus 2 is a second order resonance with e squared terms appearing, e being the eccentricity, and so on. So for quasi-circular orbits, like we often find in these systems, most of these terms won't be important. And I said that, there's this rich theory of how to handle Hamiltonian or quasi-integrable or perturbed Hamiltonian systems. That's all quite theoretically nice, but often in practical applications, the huge headache is getting these coefficients, of course. And so that is where Selmec comes to the rescue. It can calculate these coefficients for you for free, or calculates these coefficients and adds them and constructs equations of motion that we can then integrate. Okay, so I'm going to walk through a series of models that we're going to then compare to numerical results. And the first thing we'll do is make the simplest model we can think of, which is the model that only includes the nearest first order resonant terms. So remember I said we're spacing our systems that we set up so that the period ratios between adjacent planets are constant. So I'm going to represent models on this period ratio of one pair versus the period ratio of the next pair plane. And our initial conditions will run through this dashed gray line. And say if we had an initial condition here, I would add terms associated with this particular resonance here. And so just to give you a quick sense of what this looks like in practice with Selmec, you don't have to absorb any of the details, but it's just a few lines, and we've added the 8 relevant terms that appear in this perturbing potential that we're adding. And when we then take the equations of motion that one gets from adding those terms and integrate them with respect to time and measure which systems go unstable, you see we do a pretty poor job. We don't really reproduce the instabilities that we see in the numerical results at over most of the range, and only find instability very near the resonances that we are including. Okay, and so the next thing one would think is let's add the next nearest first order resonant terms. And so now this now includes 16 total terms, and we're starting to reproduce instabilities across the period ratio range that we're exploring, and we're getting satisfactory agreement with the trend that we're seeing. And okay, we can keep going, and now our model is up to 28 total terms. We've added now the second order resonance terms, which I've marked in blue for the nearest second order resonance, and we get good agreement. Okay, so what is the point of all this? Have we just traded one set of numerical results for another? know, once you have this minimal dynamical model, with a little bit of extra effort, you can derive how instability time scales should scale with the parameters of your system. So based on the equations that you develop with this minimal model, you can show that the quantities that are dynamically important are the mass, planet-star mass ratios and fractional semi-major axis separation in this combination that I've written here. And you can show that the dependence on planet eccentricities should only enter in this ratio of eccentricity to the fractional orbit separation. And to underscore this point, we're showing a series of numerical simulations now spanning 4 orders of magnitude in planet mass. So each set of colored points corresponds to a different mass, a set of planet masses in this same experiment. And now you can see when you plot them on this plot in the appropriate variables that we derive from this model, they basically lie more or less on top of one another. And one can go even further with this sort of minimal model and develop a completely analytic theory of where you expect to find dynamical chaos in these systems. So this is taken from that math paper that I showed earlier, where using a very similar minimal dynamical model, we're able to predict where we expect chaos to occur, and our prediction is shown on the plot over there in red. And you can see we pick out essentially almost all of the fine feature that you see in this period ratio plot that was derived from direct numerical integration. And so I think this underscores the value of having this sort of minimal dynamical model from which to start from. And it really serves as a starting point for developing a more complete theory that really gives us access to the sort of questions we want to answer about planetary systems and how they've evolved. For example, you can use this as a starting point for understanding what sets the timescales to collisions in systems, or which planets in a given system are most likely to collide with one another, what sort of orbits do they end up on afterwards. And you can even extend the same formalism to start dealing with the evolution of planetary spins and how they couple to their orbit as well. So, having this tool to run numerical experiments and sort of develop theory from a minimal dynamical model is really the way forward, I think, for making sense of the systems that we have today. And so now, in the last part of the talk, I want to describe some exciting opportunities, I think, that are coming up for using dynamics to learn about the types of planetary systems that we'll be discovering in the near future. And one particular type of planet that I'll be focusing on are those planets discovered by microlensing. And that's because in 2027, NASA is set to launch the Roman Space Telescope. This is a near-infrared mission that is going to projected to detect over 1,000 microlensing planets. And the way this works is that basically Roman will stare at a background field of stars, and every once in a while we'll get lucky, and a star and its planet will pass in front of that background star, and through general relativistic effects will act as a gravitational lens that causes this brightening of the background star. And by analyzing this characteristic brightening pattern, one can measure both the mass and planet-star separation of a given planet. And so this method is particularly sensitive to planets at separations that we've really been blind to up until now. This is illustrated by this projection plot taken from a paper by Penny et al. 2019, where they show projected detections from Roman, and you can see we're really pushing out into separations similar to our own outer giant planets. And we actually push down to quite sensitive to quite low mass planets at those distances. Okay, so this is great. The downside, of course, is that what I'm plotting is really basically the only thing that Roman will give us for most of these planets. we'll get a mass and a planet-star separation. And that's kind of far from the sort of questions that we'd actually like to learn about in these systems. For example, how many planets do these systems typically have? What sort of orbits are they on? What sort of orbits did they form on? And how do they compare as a system to our own solar system? And I'll argue that understanding dynamics and instabilities in particular will be an essential tool for understanding these detections. And that's in large part because in addition to all these planets around stars that women will find, it will also be a great tool for finding free-floating planets. These are planets that are just out floating unbound to any star. This works by microlensing just like a single star does. So occasionally we'll get these fortuitous passages of free-floating planets from the background stars that allow us to learn about their masses. And there's already evidence based on current microlensing surveys that there's a large population of free-floating planets. This is results from the latest results from the MOAA, is a microlensing ground-based survey that looks for microlensing. And based on their statistics, they estimate that there's something like an astounding 20 free-floating planets per star, down to at least a third of Earth mass, which seems like an incredible number of planets to just be out there floating free. Assuming these all formed around a star, how do you unleash 20 planets out into space from a system? And if if their estimates hold up, then it's expected that Raman should detect something like 1,000 such free-floating planets. And so, assuming these planets form around stars and are lost in instabilities, we know that they can't originate from the sort of systems that we see today, formed at the sort of sub-Neptune distances, and that's because, yes?
How do you define a free-floating planet if it's associated with a star?
So a free-floating planet is one that's not gravitationally bound to a star.
But then how are the statistics like for a star or?
Oh, we know the sort of density of stars in our galaxy, and then based on, so they count up their detections and say, based on the number of things we detected, this must be the density of free-floating planets based on the microlensing events that we measured. Yeah, yeah. And so we know free-floating planets have to come from further out in planetary systems because of the physics that's encapsulated in this so-called Safronov number. So this is a ratio of energies. It's the ratio of energy to escape a planetary surface relative to the energy required to escape its star's potential well at its orbital location. And so when this ratio is less than 1, then when planets are unstable and scattering one another, a scattering planet will never manage to excite the velocity of something it's scattering above its own escape velocity, and before it ends up colliding with whatever it's scattering. So Safronov number below 1, you wind up with a collision, and then however further distances, your planet is so geometrically small relative to the scale of its orbit that while it's gravitationally scattering, they'll basically effectively never see one another, and these instabilities will ultimately wind up in ejections. And so as a simple illustration of this fact, I'm showing a numerical simulation run by undergraduate student I'm working with, where he set up, so Ethan set up a 3-planet system comprised of a Jupiter set out at 30 times the Earth-Sun distance. That's where our own Neptune is, for reference. And he lets it go, and in less than 100 million years, the Jupiter has made short work of the Neptune planets and ejected them from the system, so they'll go on to be free-floating planets kicked out of the system, and the Jupiter is left behind. But the Safronov number is not the whole story in these systems, and that's because of timescales as well. So here is a second simulation where now it's a system comprised of 3 Neptune mass planets rather, set up at the same distance. And this system is set up so that it goes unstable after roughly 1 billion years. I should say, plotting the semi-major axis versus time, and then the sort of band of color is the closest and furthest approach of the elliptical orbit. So when it becomes eccentric, this band sort of fills up a region here. But what you see is that after the system goes unstable, they start sort of kicking each other around and sort of doing this chaotic scattering dance, but nobody ever gets kicked out, at least for a couple billion years. And if one were to look at, say, some random time while they're undergoing this sort of scattering, then you would find some system with sort of very eccentric and misaligned orbits, and potentially Neptune-mass planets at far distances from their star. Okay, and so, understanding this dynamics, especially the sort of quasi-random chaotic scattering that these systems undergo, and the timescales, for example, that it takes to eject things, and how it depends on planet masses and distances and the number of planets in a given system, I think is really the way that we can make a connection between the population of free-floating planets that we detect and the systems that we know they must have left behind. And we know that, of course, both of these populations will be represented among Raman's detections. So I think dynamics provides one of the best windows into trying to learn something about what goes on in the outskirts of planetary systems from the simple mass and separation measurements that microlensing will be providing us. And of course, with 20 free-floating planets per star, you have to wonder, did it happen here? That's a lot of planets to kick out. Did we do it too? There's popular models of solar system formation that invoke some instabilities that may have kicked out an additional ice giant planet. And all I'll say about this is that if we did, there should be all sorts of dynamical traces left in the distribution of small bodies in the outer solar system, the so-called trans-Neptunian objects. If you're kicking around planets for a prolonged amount of time, it's going to make a mess of the orbits of these small bodies, and we'll have an excellent chance to probe this orbital distribution thanks to LSST, which should see first light, I believe, next year, which will discover over a factor of 10 increase in the number of these TNOs we know about. However, to make sense of the orbital distributions that we observe, we really need to disentangle dynamical footprints that may have been left by these instabilities from the natural and complicated chaotic evolution that these bodies experience just by virtue of being perturbed by Neptune and the other giant planets in particular. And I'm happy to talk about this more later. This is something I've worked on recently, but I'll leave it at that for now and just leave you with my conclusions, which is that understanding how planetary systems have come to be the way we see them today really requires understanding how they've evolved over their full multi-billion-year lifetimes under gravitational dynamics. And I made the case that using computational implementations of dynamical systems ideas is really our only way forward, I would argue, for understanding the sort of complicated evolution of these planetary systems. And this sort of dynamical understanding will continue to be essential as the discovery frontier pushes out in both the solar system and exoplanets. So thank you.
So I'm trying to formulate this question. I'll do it in real time. So in the second part on Hamiltonian perturbation theory, you showed us that that you compare the dynamical system way down to considering just a few resonances. Yes. And one of the benefits of that was to identify what dynamical quantities are important and what are not. Yeah. Is that the goal, or is that the only goal, or is it also computationally much more efficient to take that approach?
Yeah, so the computational efficiency, you can, so it actually turns out that, when you add 28 cosine terms and just throw it to an off-the-shelf Lambda-Kutta integrator, it can get less computationally efficient than full integrations, but there are actually lots of avenues for making this more efficient than direct simulation. So for example, at the very beginning, I mentioned that Lascar work where he used so-called averaged equations. So he did something analogous to this, and the reason he was able to do billions of years of solar system integration when nobody else could at the time is because he was basically taking this approach. And so, for this particular piece of work, we didn't expend a lot of effort into making the computations efficient, but I think there's a lot of avenues for doing so going forward, and that I think is something I plan on working on, as well as having numerical methods. Say analytic theory just is a dead end or hits a wall at some point. It won't be, but at the same time we can also push numerical methods beyond what we can do with direct integration with this technique.
So along those lines, then, I've been told that quantum computers are going to be the bee's knees for integrating Hamiltonian systems. Is this the kind of system that you could solve with a quantum computer?
If it is true that quantum computers are the bee's knees for integrating Hamiltonian systems, then yes. This is as Hamiltonian as it gets. This is the original Hamiltonian system. I'm not familiar with the particular
Hamiltonian system. That is exactly.
I mean, we could also build classical Hamiltonian computers. Why go quantum? It's way easier to build a classical Hamiltonian than a quantum Hamiltonian.
No, he's talking about a quantum computer.
Quantum computers do.
I know, but I'm saying, why not build if what you want is Hamiltonianness, let's build a classical Hamiltonian computer.
You mean like an analog computer?
Yeah, an analog dynamical computer, yeah. I mean, that's got to be easier than a quantum computer.
Is it easier than a digital computer?
No, way harder. But quantum computers don't even exist, so,
Right, but it's a totally different. It's still a numerical calculation on a quantum computer.
Right.
So
I think there's
but the thought was that you get to the answer without having to do the iterations. So in principle, it could be ridiculously
because
more.
it's a Hamiltonian math.
Yeah.
So one idea is that I think, so certainly with these methods, you can take much larger time steps, and what sort of makes it hit to the efficiency now is just the force evaluation, because you're integrating 28 or evaluating 28 terms. But that's something I think can parallelize much more easily. You can sort of organize these terms individually so that they're maybe evaluated in some parallel fashion. So yeah, I mean, direct numerical integrations really can't take advantage of parallelization, which has really been the way that computing has made progress for the past 20 years.
I would return, there was a confusion in the room that was started by Eric Vandeninen, which is about the sensitivity to your perturbations.
Yes.
And my point of view is that the reason that it doesn't matter whether you perturb it by 1 millimeter or 10 millimeters,
right, is
that for me, my intuition is that it has something to do with the Lyapunov times. That's why I asked you at that moment about Lyapunov times, because the Lyapunov, you didn't talk about this, but the Lyapunov times are shorter than the overall stability time.
Yes, yeah, that's actually.
The Lyapunov time is like millions of years,
that's
the
right.
stability is billions of years. So that's in my view, but maybe you could just come back to that question and see if you can resolve this question. Because when you say, things are going to diverge exponentially from the initial conditions, then it sounds like if you move it by 3 times as much, it should diverge twice as quickly, which it does not.
Yeah, this is linear behavior. So this is when linearizes about a trajectory, the divergences. So that's what's unlike. Is what happens after.
In a similar spirit, a crazy question, but in the spirit of equating chaos and probability, right? Yes. Can you develop a stochastic model that could solve things in a faster way?
Yeah. So the work that let me go back up to this. So I alluded to this work on dynamics in the outer solar system. And there, this was recent work we did. The evolution in so it's this so-called scattering disk. These are bodies that are basically kicked around chaotically by Neptune and the distant solar system. And so they get on these really large orbits, but always come back to the same pericenter, basically. And we showed that you can describe the evolution of these bodies as basically a random walk in energy. You can derive a Fokker-Planck treatment for the diffusion in energy, and you can even go and derive the diffusion coefficients as a function of, it's actually an energy-dependent diffusion coefficient, and it depends on the particular orbit. And yeah, describing chaotic systems as random processes, I think, is, they exhibit all these interesting behaviors that typical random processes don't. In this case, it's very nearly just a sort of Brownian, or mathematicians have physicists have different words for exactly what type of random walk they're talking about. But there's some funny phenomena, like actually in some work with John, we showed that Mercury, for example, exhibits subdiffusive behavior in some particular dynamical variables. And you find all sorts of anomalous diffusion in Hamiltonian chaotic systems. And yeah, you know, for a random walk, right, you should have sort of exponential decay and escape time for things escaping, but you can end up with power law tails for things that stick around for a long time. And there's all sorts of interesting stuff, I think, to do with understanding effective descriptions for chaotic Hamiltonian systems as random processes.
So could you use something like large deviation theory to predict what is the earliest time to escape average? If you model it.
Presumably, yeah. I mean, this is something I've talked about with John a little bit. Yeah, I think that's a promising possibility. But you know, we're not always interested in first time. If you're interested in, say, explaining the population of exoplanets, then, by definition, we're interested in understanding the typical behavior, say. But you know, another way to put it is, it takes one very large deviation of an orbit to end up smacking into another planet. Right. So you know, how long do you go without a sufficiently large deviation in your orbit, say, that leads to running into another planet? Yeah.
I mean, I have a million questions. Maybe other people in the room want to ask. Maybe Sir has a question over there.
I maybe said this, I'm sorry if I missed it. You said chaos is sufficient, not necessary condition for instability.
Necessary but not sufficient.
Yes.
Yes. Yeah.
Necessary but not sufficient. What is the distinction exactly? Like explicitly, what are the other conditions you would need?
Well, so that's I mean, that is an active research question. Is when. So if you just take the giant planets by themselves, actually, they exhibit chaos, but for as long as people can integrate them forward, they don't seem to ever exhibit instabilities, like large-scale instabilities. And the way the chaos manifests in the giant planet systems is that you basically lose track of the ability to track an orbital phase well. So, like, you know, you won't be able to say in 10 billion years which side of the sun Neptune is on, but it should be sitting on an orbit with basically the same semi-major axis that it has today. So yeah, understanding when, I'm just flipping through the slides. Okay, when do things actually lead to instability is an open question. Does that answer your question?
So by unstable,
I mean, like orbit, something being ejected or running into something, or usually the working definition that people use in planet dynamics is a significant change in a planet's semi-major axis. So, for example, in our solar system, Mercury evolves chaotically for a long amount of time, but it always has the same semi-major axis. So its ellipse, you know, keeps the same position, but it just stretches and sort of moves about spatially until it gets so eccentric that then basically running into Venus or being scattered by Venus becomes a problem. Yeah. So basically, anytime you have semi-major axes changing in a planetary system, something bad is going to happen to that planet.
So with your selenite code, you show you can compute the instability time as a function of semi-major axis or period.
Yeah, the way we set up the system.
Right, but can you also predict let's say you have some initial condition with the period, can you also predict for a family of orbits with that period where they will end up? So can you?
Yeah, I mean you could you mean
can you make a plot of their semi-major axis as a function of number of orbits?
Yeah, you can plot all the same basically dynamical variables that one would care about in the full in-body problem from somewhere.
So can you make a prediction for the solar system then with that code as well?
Yeah, it would produce basically what we know about the solar system already. In fact, I've used it a little bit for doing some solar system stuff. You can be clever actually and note that you can basically put the giant planets on rails because they don't really feel much back reaction from the terrestrial planets, and ask what happens to the terrestrial planets, and then there the sufficient dynamical model is a little more complicated, but yeah,
yes. How much do external factors or objects outside of the system that you're simulating affect the dynamics, like collisions with asteroids and
yeah,
I mean, we're talking about like millimeter size.
Yeah, I mean, the qualitative conclusions that one comes to don't really differ when you add this sort of small sources of extrinsic, so that's like extrinsic noise to the system, and it doesn't lead to qualitatively different conclusions about how the system is going to behave. I think.
What about radiation pressure? Over 1 billion years, does radiation pressure have any effect on Mercury? Nothing.
I mean, except for the tiny changes that it makes get blown up, but those are on par as the same uncertainty we have in its position anyway.
Because that's in a non-random. I'm thinking about forcings that aren't random.
Yeah,
you know what I mean?
Encounters with other stars would have an effect. Right?
If they come close enough, yes, that can.
Freely floating planets, all the ton of them now.
But the tidal force of the galaxy is irrelevant.
Tidal force of the galaxy does affect stuff in the scattered disk if it gets out far enough. Right? So that's actually part of the reason we have comets, is because we have all this junk out there that was probably kicked out there in instability, and every once in a while, either passing stars or the tidal potential from the galaxy causes them to dip in and close. So that's where our comets are. Long period. Yeah, so one of the big pieces of evidence for early shakeups in the solar system is that we find a long period comets that basically come from an isotropic distribution on the sky. And so there's what people call the Oort cloud, which is thought to be basically all the junk that the giant planets kicked out while they were forming and sort of dynamically shaking themselves up. So some of it remains bound, and every once in a while gets nudged by some teeny force. These things are so weakly bound that it doesn't take much to.
But the Oort cloud is not really directly observed at this point, right?
No, that's right. There's ideas to do occultation detections, and people have tried, but no luck so far. But yeah, it's theoretically inferred. And the Kuiper belt itself was hypothesized as being detected. So those are trans-Neptunian objects in Kuiper belt are quasi-interchangeable. Small body population. There's thought to be the source of comets that do come in basically in the planet solar system.
The collision with Andromeda, that's probably too diluted.
Yeah, that's we're not going to run into other stars. There's all sorts of interesting applications of this in galactic dynamics as well. It's Hamiltonian.
Can I? This is Eric van der Leyen again. Can I ask you a question? Whether there would be another way to look at this problem, particularly because there are people in audience like Stefano that they've looked at that. So the system you're looking at, being Hamiltonian, is moving on one level set of this Hamiltonian, right? So is there a way to explore this geometrically differently than by doing dynamics? Because when you integrate the dynamics, especially on these long time scales,
you need
you know, you need to rely on all kind of integrators that can be simplex or whatnot, but it's not completely clear at the end of the day whether the accuracy. Is there a way, or would there be a way to look at the problem and simply ask, you know, are the level set of this Hamiltonian running off to infinity? That would imply that they at least the possibility of escape. Are people looking at it this way or no?
So in planetary systems, which, okay, that's right. You can always have things run off to infinity, and you know you can send another planet further in. Or if you have two planet systems, so yeah, this is actually there's all sorts of peculiarities of the planetary Hamiltonian, specifically that make some of the methods for treating Hamiltonian systems, perturbed Hamiltonian systems, a little bit more difficult. One of them being that the energy surfaces are not compact.
Right, okay. Okay, I see. Okay, thank you.
Sure.
Is that really shown that, like, I agree with you that everyone believes that if you take, there's not just the energy, there's other conserved quantities. Everyone believes with that set of conserved quantities, you can still get to infinity. But is it really shown that you can always get to infinity? I don't think it is, right?
Well, that's the question, right? You mean, right, so you have what? Angular momentum, linear momentum, energy, and you're saying with those conserved quantities, is it always possible to get to infinity?
And I believe it is. But everything I've done suggests that it is, but to truly show that there's a route to infinity.
Find out later.
Yeah, that is a great question.
Yeah. Well, right. So the things that prevent you from
it's a very complicated surface because it has.
Yeah. So the question, right, is I sort of gave this crash course in perturbation theory.
So we're just seeing a white screen.
Yeah, I know. Okay, well now I'm scrolling, I think. Let's see. Right. So in the hand wavy way, sort of, if this series converges, if you can make a series like this converge, then you have additional conserved things. It has to stay on torus, basically.
Right. Yes.
This is a torus. And so the question is, do you have additional conserved things? And right, so if you, as I've written it here, this considers, stuffing in different variables into this.
Yeah.
And so you either have all the way, either you have all n of those conserved or none of them, or can you have some of them but not others? And so actually we didn't, so one of the problems in the solar system, right, it has this 5 million year sort of Lyapunov time, right? The time to lose track of initial conditions is very short compared to how long it sticks around and stays stable. And I don't think it was really understood why until actually relatively recently. And now, in a sense, you have quantities, none of them are conserved, but they sort of act conserved on a hierarchy of time scales.
That kind of has to be true, because otherwise the Lyapunov time would just be the time. There has to
so
be some quasi-conserved quantity.
Yeah, right. So it doesn't quickly, uniformly fill all available phase space.
Exactly.
Well, maybe that's a good time to stop. That was just fascinating. And you're going to be around all day tomorrow and part of the day on Thursday.
Yeah, I'll be good.
And there's a sign-up sheet, I guess, run by Tim, if people want to get to find you.
Yeah. Thanks for tracking in the snow, everybody.